As another important information, you need to understand how many vibrational modes you could have for each molecule, which can be calculated from the freedom of degree of the molecules. So, for example, if you have a water molecule, you can probably understand how many vibrational motion could be possible. But if you have, for example, 100 atoms molecules, how can you possibly know how many vibrational modes you could have for the molecules? So here's how to calculate to know how many vibrational modes for the molecule have. So this is how to consider it. So so each of the molecule need to have the freedom of degree, and if you have n atom molecules, this molecule need to have 3 times n freedom of degree is necessary because each atom need to have a 3-dimensional freedom of position, right? So when you need to define the molecules, you need to decide 3n number of freedom of degree. Another way, each atom, so n atom molecule have 3n freedom of degree. So thinking this one can be understood based on the motion of the freedom, because the position of the freedom of degree is the same as motion of the freedom of degree, and each molecule has 3 translational velocity in x and y and z direction, right? So the translational velocity, and also if you think about the rotational motion, and you could have x and y and z axis rotation for a nonlinear molecule, and for a linear molecule you have 2 rotational motion, because if the linear molecules, and if you take the rotational axis same as the molecular axis, there's no rotational motion. So you have 2 rotational motion for linear molecules. So in that sense, but still you have to have 3n freedom of degree. And then in the case of nonlinear molecules, still you have freedom of the motion is 3n minus 6. And for linear molecule, 3n minus 5 linear motion mode must be. So based on this calculation, you can calculate the vibrational mode, because in each molecule you could have three motion state, like translational, rotational, and a vibrational motion. So in case of water, this water molecule is made of the 3 atoms and nonlinear molecule, right? So it means 3 times 3 minus 6 equal 3 vibrational modes you could have. So you need to think about 3 different types of mode actually, and this water molecules have symmetrical oscillation and angle changing oscillation, and asymmetrical oscillation you could have. And here's another topic, but I will cover this. which is a vibrational rotational spectrum, meaning the coupling of the vibrational energy and the rotational energy. And always, each molecule not always have a vibrational oscillation and also rotational motion too. So, in fact, the energy of the vibrational and rotational can be plus how mu plus b j plus 1. So this is vibrational, this is rotational energy, and they could be coupled. So from the transition law, when the vibrational energy is increasing 1, the delta J, meaning the J rotational energy, can remain or change +1 or -1. So what it means is, depending on the rotational energy change, there are three different absorption when you observe this rotational vibrational spectrum in the infrared absorption. So what it means is, you could observe, like, center that the absorption spectrum of vibration here. You could have many fine structure of the absorption in the higher frequency region and lower frequency region. So what it means? So here's a vibrational ground state. Here's a vibrational excited state. And you could excite without changing the rotational energy state, meaning delta J equals 0. So in this case, so from 0 to 0 and 1 to 1, right? So 2 to 2. So 2 to 2. Oh, that's changing. Okay. So here, so without changing the J value, the profile of absorption spectrum is almost constant, which is called Q branch. But on the other hand, every time you could increase the delta J is larger, which is if this one, this side, yes. So from 0, okay. From 0 to 1 is here, right? And 0, so 1 to 2. So 1 to 2. Actually, this one is mistaken. So 1 to 2 and 2 to 3. 2 to 3. But on the other hand, this side is opposite. So 1 to 0 and 2 to 1, 3 to 2, something like that. And this one gives a lower energy of side, P branch. And this could be confirmed by just calculating that mu of J equal V plus 1 J minus 1 minus S Bj, which is centered at mu minus 2Bj. So every time J changed, the energy level is changing. That's why you could have this type of the different fine structure. But if there's no change in the J value, there's no change in the J value, mu of J as void plus 1 J minus S3J, which gives always mu. And similarly, mu of J, when the J is increased, plus 2Bj. So that's why you could see these kind of fine structure. But if you have an experience of measurement of the infrared absorption, probably you've never seen this fine structure. This measurement could be only possible if the spectrometer has a very high sensitivity, or there's no very low temperature is necessary. Otherwise, it's going to become a very broad absorption, just give a broad absorption. So what's that? So we in this lecture we study the vibrational oscillation level, how to calculate the energy and introduce Morse potential, and also how to calculate the number of mode and vibrational rotational spectrum and so on. And then in the next lecture we are going to finally move on to the optical absorption.